You stepped outside this morning and felt the ground beneath your feet. Solid, certain, real. That feeling of weight pressing you down into the earth is gravity doing what it always does, quietly, invisibly, relentlessly pulling you toward the center of something massive. Now imagine that same force cranked up to a level your brain was never built to understand. Imagine a place where gravity becomes so extreme that not even light can escape, where the very fabric of space stops bending and simply ends, where the laws of physics as you know them, every equation, every prediction, every certainty, break down completely. You are thinking about a black hole. And today, you are going to fall into one. Not a metaphor, not a thought experiment described in vague terms. You are going to follow the physics step by step from the moment you cross the point of no return to whatever waits at the other side of everything science currently understands. Fasten something. This will be strange. A black hole is not a hole. That is the first thing to correct. It is an object. An extraordinarily dense object with a gravitational field so powerful that the escape velocity at its surface exceeds the speed of light. Since nothing in the universe moves faster than light, nothing that gets close enough can ever leave. The boundary that marks this point of no return has a name. It is called the event horizon, not a wall, not a surface you can touch. It is an invisible line drawn in space where the geometry of the universe changes so fundamentally that every path forward leads only inward. The physicist Carl Schwarzschild calculated this boundary in 1916, while serving in the German army during World War I, writing his equations from the trenches. He sent his work to Albert Einstein, who reportedly could not believe the math was real. It was. And the radius Schwarzschild calculated to describe the size of the event horizon still carries his name today. Now, you are traveling in a spacecraft toward a supermassive black hole. Not a small stellar mass black hole of a few solar masses, but a true giant, billions of times the mass of your sun, like the one imaged by the Event Horizon Telescope team in 2019 at the center of the galaxy M87. A black hole so large that the tidal forces near its event horizon are actually manageable. That detail matters. You will see why. From far away, the black hole looks like nothing at all. Space is dark, but then your instruments begin to behave strangely. Light from stars behind the black hole bends around it, creating rings and arcs and phantom copies of stars that do not exist where they appear. This is gravitational lensing. The black hole is using its gravity like an enormous distorting lens, warping the path of every photon that passes nearby. The closer you get, the more extreme this effect becomes. Stars seem to swim and shift. The darkness at the center of your view grows. It is called the shadow. It is the region where light that tried to escape was pulled back in. You are looking at the outline of the event horizon itself. Someone is watching you from a safe distance. Your friend, your colleague, someone who stayed behind with a powerful telescope trained on your ship. From their perspective, something very strange is happening to you as you fall. You are slowing down, not because you are actually decelerating, but because gravity curves space-time itself, and one of the consequences of that curvature is time dilation. The deeper you fall into a gravitational well, the slower time moves for you relative to someone far away. Near a black hole, this effect becomes extreme. As you approach the event horizon, your friend watches you move slower and slower, like a video being stretched toward a freeze frame. Your image reddens as the light from your ship loses energy, fighting to climb out of the gravitational field. Eventually, from your friend's point of view, you appear to stop completely. Frozen on the edge of the event horizon, fading to red, never actually crossing. They will never see you fall in. But you do. From your own perspective, inside your ship, falling freely, you feel nothing unusual as you cross the event horizon. No alarm, no wall, no physical sensation to mark the moment. This is a crucial insight from general relativity. In free fall, you are weightless. You are following what physicists call a geodesic, the straightest possible path through curved spacetime. The event horizon is not a place you feel. It is a place you pass. Stephen Hawking, who spent decades building and refining our understanding of black hole physics, described the event horizon as a one-way membrane. Information crosses it freely in one direction. Nothing crosses back in the other. You have crossed it now. Look back. You can still see light from the outside universe. It floods in through the event horizon from every direction and collects into a bright shrinking circle above you. The entire outside universe, compressed into a single shrinking window of light at one end of your sky. Below you, if below still means anything, is darkness. And something is pulling. Not painfully. Not yet. But the curvature of space-time inside the event horizon is extreme and growing. Space itself is flowing inward, toward the singularity, faster than light. The singularity is not a place you are falling toward in the way you fall towards the floor. It is a place you are falling toward in time. In the same way that you cannot avoid tomorrow, you cannot avoid the singularity once you have crossed the event horizon. It is your future, mandatory, unavoidable. For a large black hole, you might have hours of proper time before you reach it. For a stellar mass black hole, it could be milliseconds. Then comes spaghettification. This word sounds absurd. It describes something that is not. Gravity does not pull every part of you equally. It pulls harder on the parts of you that are slightly closer to the source. Near an ordinary planet, this differential, called the tidal force, is too small to notice. Near the singularity of a black hole, it becomes catastrophic. Your feet, closer to the singularity, are pulled harder than your head. The difference grows exponentially. Your body, and then the atoms of your body, are stretched vertically and compressed horizontally into a long, thin stream of matter. Astrophysicists confirmed this process observationally when they detected tidal disruption events, moments when a star gets too close to a black hole and is torn apart and consumed. The flare of radiation from a single star being spaghettified can briefly outshine an entire galaxy. You are experiencing, in a personal way, what those stars experienced. At the singularity itself, physics stops. The equations that describe space-time, the equations of general relativity, produce infinity, infinite density, infinite curvature, infinite tidal force. In mathematics, infinity in a physical equation is a signal. It means the theory has broken down. It means something is happening that the theory was not built to describe. Roger Penrose, who won the Nobel Prize in Physics in 2020, specifically for his mathematical proof that singularities are an inevitable consequence of general relativity, described this as an edge of spacetime. Not a place inside space, but a boundary where spacetime itself ceases to exist. What happens there, no one knows. String theory offers possibilities. Loop quantum gravity offers others. Some physicists propose that the singularity is replaced by a quantum mechanical bounce. That matter is compressed to a maximum density and then explodes outward, possibly seeding a new universe inside the black hole. This is not confirmed. It may never be confirmed. Whatever happens at the singularity is, by the definition of the event horizon, forever hidden from the outside universe. This is why Penrose and Hawking both believed in what they called cosmic censorship. The idea that nature always hides its singularities behind event horizons, keeping the breakdown of physics safely out of view of the rest of the cosmos. There is one more thing about black holes that almost no one tells you correctly. They evaporate. Hawking proposed in 1974 that black holes are not permanent. Due to quantum mechanical effects at the event horizon, black holes slowly radiate energy, now called Hawking radiation, and over an almost incomprehensible span of time, they shrink and eventually disappear in a final burst of energy. For a black hole the size of the one you fell into, the evaporation time is longer than the current age of the universe multiplied by many orders of magnitude. But it is finite. The black hole ends. And when it does, a question that has tormented physicists for 50 years remains unanswered. What happened to everything that fell in? The information paradox. Everything in quantum mechanics says information cannot be destroyed. Everything about the event horizon says it cannot escape. The two pillars of modern physics, quantum mechanics and general relativity, directly contradict each other on this point. We do not have the theory that resolves this, we are still building it. Which means that somewhere inside everything we think we know about the universe, there is a door we have not opened yet. You stepped outside this morning and felt the ground beneath your feet. That ground is made of atoms forged in stellar cores, scattered by supernovae, pulled together by the same gravitational force that carves event horizons across the universe. Gravity shaped every atom you're made of. It has been with you since before you were born. And somewhere out there, in the center of your own galaxy, 56,000 light years from where you are standing right now, there is a black hole 4 million times the mass of the sun, quietly bending the fabric of space around itself. The ground still feels solid. But now you know what solid really means.